Okay, so we're just going to finish up the last few problems on the chi-squared review solutions. So we were right here where we were talking about the number of female and male students and how many of them chose engineering. So the number of female engineers is expected to be this percent, 80 divided by 400, times the number of female students, 180 divided by 400. So if we multiply those two percentages together, we're going to get a percentage of female engineers, okay, and then we're going to multiply that times the total number of students, and we get 36. Okay, so that's maybe not the number of female engineers, but that's the number of female engineers that we would expect, given that there's 80 engineers and 180 female students. So, combining those two percentages, we would expect to get 36% if there's no relationship between female, male, and engineer or not. So then we are going to analyze the actual distribution to see if it's really independent or not. And we don't actually have the actual distribution in this case, but they do tell us that the p-value obtained during the chi-squared test is 0.0634. 0.0634 is pretty small, but we don't know if it's small enough to prove that the distribution is independent or not. We need to compare the 0.0634 to 0.05. Why to 0.05? Because they said it was going to be a 5% level of significance, and so that would be 0.05. Now, is 0.0634 less than 0.05? No, it's not. It's greater than. Actually, the p-value, if it's small, and so small that it's below the significance level, then it is, that means you can reject the null hypothesis and it's dependent. But in this case, the p-value is bigger than 0.05. So that means that we do not reject the null hypothesis. We accept the null hypothesis. So profession is independent from gender. So it is independent. Okay. Now we go to number 4. Number 4 is kind of different than the problems we saw in our book, and the reason why is because we don't have a table which has two variables. We only have one variable. We just have the variable color, right? And you can do chi-squared tests on distributions that have just one-dimensional tables. It's a little bit different. We're not going to really talk about how to do that here. What we're really interested in is something that you're going to need to know for your internal assessments, which is that when you do a chi-squared test, you need to be careful that you have enough frequencies in each one of these cells that they're not too small, okay? Because if they're too small, you might not be able to use the chi-squared test for that distribution. The distribution needs to be fairly large, and when I say fairly large, I mean that the expected value for each one of these cells should be 5 or more. Okay, so that's what this problem is looking at, whether or not the expected frequency for each of these cells is at least 5. And if it's not at least 5, how do you handle that? Well, normally what you do is you take one of the smaller cells and then you combine it with another cell. So instead of saying blue, we're going to say blue or purple. We're going to combine these in the same cell, and this total would be like 15, for example. Okay, so a bag of 60 sweets is open. The bag contains sweets of the following colors, and this is their distribution. So this is the observed distribution. Later it says, according to the manufacturer, the various colors should have the following percentages, and it gives percentages as to what the distribution should be. And so it says it should be 35% red, 25% orange, etc., 5% blue. Okay? And A says, calculate the expected number of sweets of each color in a bag containing exactly 60 sweets. Okay, so whenever we do a chi-squared test, we are comparing the observed distribution to an expected frequency distribution. Expected frequency distribution can't be a percentage. It must be a number. So what we do is we multiply each one of these percentages times the total number of 60, and that gives us the expected frequency of each color. So red would be 21, orange would be 15, and that's assuming that you have 60 total candies. So what we see here is that blue, the expected frequency is only 3. And then for part B, it says, before you can perform the chi-squared test on this data, is it necessary to combine the data for one of the colors with that of another color? And so, we see here that for blue, the expected frequency is 3, which is smaller than 5, and the rule is that the expected frequency should be 5 or more. So it says, do we need to combine any of the colors together? And yes, we do, because blue, the expected frequency is 3, it's too small. We need to combine it with one of the other colors. It could be any color, but maybe what you do is you combine it with the color that is the second smallest, which would be purple. So you could say that blue has an expected value of 3, which is very small. Expected value should be at least 5. To be able to use the chi-square test, you should combine blue with purple or another color to make sure that each expected frequency is greater than 5. So if you combine blue with purple, then the expected frequency of both would be 12, so then you would be fine for chi-square test. Okay. Now for the last problem. This is looking at how you calculate chi-squared. In this problem, they look carefully at how chi-squared is actually calculated. And your calculator does this automatically, but in this problem, you can't really use your calculator because it's looking at it more in detail. And basically, when you calculate chi-squared, what the calculator is doing is it looks at the two tables that you have, and when you have the tables, you really only have one table, which is the observed frequencies. Okay, so let's say that the table that the problem gives you is 36, 27, 22, 35. Well, remember that whenever you have a table that they give you, there is also another table which your calculator calculates to calculate the chi-squared value, and that is the expected frequencies. And the expected frequencies, as we talked about in the other problems, what you do is like for example, if I want to calculate the expected frequency of getting a heavy puppy from a heavy dog, I would calculate the percentage of, the total number of dogs relative to the total births and the total number of puppies for that category relative to the births. So for example, to figure out what the expected value here for 36 would be, I would calculate 63 divided by 120 and multiply that times 58 times 120, because basically I want to know what percentage of the puppies are heavy, what percentage of the dogs are heavy, and then I would multiply that together to see how many heavy puppies do we expect to get from heavy dogs. And so that would be 63 divided by 120 divided by times 58 divided by 120, and that would give us 30.45, for example. Okay, so that the table that we would expect for the expected frequencies, we would construct that way. The calculator, of course, does that calculation automatically. And in this problem here, it gives you all these values except for one, and it wants you to calculate the other value. Well, your calculator can calculate some of these values, okay, but some of it doesn't show you, because the calculator it calculates the chi-squared, but it doesn't show you all the intermediate steps it uses to calculate chi-squared. So, okay, let's go to this problem then. So the veterinarian wishes to test the hypothesis that a puppy's weight is independent of its parent's weight. Okay, well, that's the null hypothesis. And so to do that, makes this table: heavy mom, light mom, heavy puppy, light puppy, sees if there's any kind of relationship there. The expected values we are expecting to see are 30.45, 32.55, 27.55. How do I know? Well, I got it out of this table here. So because the table gives us the expected frequencies, FE. for each of the observed frequencies. So I filled in 3 of the values. Now it doesn't give us A. What it asks us A later. It says write down the values of A, B, C, D. So what is the value of A? Well, there's 2 ways to get that. One is your calculator. If you put this table in there, 36, 27, 22, 35, in your calculator, it's going to give you that. Distribution, the expected frequency distribution. So, and I'll show you how to do that here. Second matrix, and we'll go to edit. And in A, I'm going to put a 2 by 2 table. And the 2 by 2 table is going to have 36. And it's going to have 22. And it's going to have, 22. And it's going to have 27, and it's going to have 35. And I'm going to run the chi-squared test on it. So I go to tests, and then I go down to the C option, which is chi-squared test, and I put in that the observed data I put in is 8, A in the A table, and the B table is empty, and I'm going to fill it in with the expected frequency, which is this table here, which I know all the values except for 1 because they gave them to me. Now the chi-squared value in this case is going to be 4.12. The p-value is going to be 0.0423. I don't need it because they're not asking me to find that yet. So now I'm going to look at the value that I filled in here for B, because in B I have the expected frequencies, and you can see the 3 values they gave us are correct: 30.45, 27.55, 32.55. The only one they didn't give us is 29.45. Okay, and if you, there it is. And if I wanted to calculate 29.45, it would be pretty easy to do because we know the subtotals, right? And if we know the subtotals, then all these columns and rows have to add up. So 32.55 plus A has to be 62. So A is 62 minus 32.55 is 29.45. So you could find it with the calculator, or you could find it, using this method here. So A, we can figure that out pretty easy. Now B is just FE minus FO. And we know each of those values, so we just take 29.45, which we get from our calculator from this calculation. We subtract 35, which we get from here, and then that gives us negative 5.55. So B would be negative 5.55. Now what about C? Now C is just saying, now take FE minus FO and square them. FE minus FO we know is negative 5.55. So if we square negative 5.55, we get 30.8025. So C is 30.8025. What do you know? Like, they're all 30.8025 because they're all, the difference between any of these are either 5.55 or negative 5.55. So all the squared values are the same. So remember when you guys made your own dependency indicator, you figured out the difference between the expected value and the observed value. That's what Pearson did too, except Pearson squares it so that he always gets a positive number. Then he just divides it by FE. Now FE is different in each case, so that's why FE minus FO squared divided by FE is always different. And in the case of this line, we're dividing by 29.545, which is FE, and then we get 1.05. And then what is the chi-squared value for this? Now we're just going to add up all these numbers. We just figured out that D was 1.05. So if we add all those up, we get 4.126. How many degrees of freedom for the contingency table? This table is called the contingency table, by the way. We never call it that in class, but sometimes they call it that. The degrees of freedom is just 1 because it's a 2 by 2 table, and there's 1 degree of freedom in a 2 by 2 table, right? You take the number of rows minus 1, number of columns minus 1, multiply them together. That gives you the degrees of freedom. So 2 minus 1 times 2 minus 1 is 1. So degrees of freedom is 1. Then the critical value for the 5% significance level is 3.84. Should we accept H0 or the null hypothesis? Well, the chi-squared value, if it's greater than the critical value, then we should reject, okay? And our chi-squared value is 4.126. We're going to compare it to the critical value, which is 3.84. it's slightly bigger. So since chi-squared is big, it's so big that it's bigger than the critical value, we're going to reject the null hypothesis. So there is a relationship between parent's weight and puppy's weight. It is not independent.